Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. Thanks for joining us for another Tuesday live stream. Now today I'm bringing you a topic which I think is appropriate for the times in which we're all working, and that is there's a lot of supply chain issues out there. And as automation engineers, as application engineers, these days we're often asked to deliver a project in which we don't have available to us, at least not in a timely fashion, the products we normally might use to solve the application. So it means a lot of thinking outside of the box. Now today's topic, it's all about using the XLEe as remote I/O. Now what is it about the XLEe that can make it an effective remote I/O block, even though you normally might use it as kind of a low-end controller? Well, we're going to explore that topic for you today. Now, we did pre-record today's session, but we're streaming it live Tuesday at 2 o'clock as we always do, and we have experts standing by that can answer your questions in the chat section. Now, if you're watching this on replay, still give us your questions. We'll just get them answered from the comment section in a timely fashion. Okay, let's dive right in. Okay, let's take a look at the breakdown of our topic today. All right, we're going to talk about why the XLEe as remote I/O makes sense, right? We'll also talk about PLCs and controllers that can be used with the XLEe as remote I/O. What are your options there? We're going to talk about the steps required to program or configure the XLEe as remote I/O. And as always, we're going to get into some hands-on demonstrations. We're going to show you a quick and simple setup, kind of one you would make if you just want to get the project done fast, specifically for your application with a minimum of extras. And then we're going to talk about or demonstrate or show you a more comprehensive setup with a few more bells and whistles at runtime. All right, let's dive right in. So why the XLEe as remote I/O? Well, let's start on the I/O side, right? That's where it makes sense to start. In some ways, the XLEe offers a mix of I/O that's roughly equivalent to several I/O modules or even a small rack of remote I/O or expansion I/O. It offers 5 different options with anywhere from 22 to 42 I/O points. You've got DC or relay outputs to choose from. You have both digital and analog points in every model that's available. You've got high-speed counting options. You've got high-speed output options. You've got temperature sensor options, RTDs and thermocouples. It's just got really great, really compelling I/O options available, and that's really the first thing you need with a remote I/O block. The next thing we're going to talk about is just the different options you have to connect from an XLEe, especially now for the last several years that the XLEe features Ethernet built in. You can interface with an ever-growing list of third-party PLCs and controllers. So if you need to interface with Rockwell, you've got Ethernet IP built in. With Modicon, Modbus TCP. Have some Emerson or GE projects out there? Well, Ethernet Global Data is kind of a native Emerson or GE protocol that's available in the OCS. How about a application that maybe involves a European drive or a European PLC and can open is the requirement? I know here in the States that may be not as common, but the XLEe does can open just great. And really, just about any modern PLC or controller is going to support Modbus TCP, which can kind of be the default way that you interface with a lot of these third-party controls. And then, hey, let's talk about the application where you just need to interface with Horner OCS, and maybe it's not even a supply chain problem because our products are pretty available, but you take a look and you determine that, the XLEe I/O mix for that particular model really solves my application really well, maybe even better and at a lower price than a whole rack of SmartRail I/O in that particular case. So plenty of options, of course, if you're connecting an XLEe as a remote I/O block, even off of a larger Horner OCS. The next thing to consider is that the XLEe is completely suited for DIN rail mounting. So, most of the time when we're installing I/O, expansion I/O, remote I/O, etc. with an automation system, we're installing some sort of I/O on DIN rail, whether it's in the same panel as our main PLC, whether it's remotely located, whatever the case may be. And the XLE, along with our other quartered-in controllers, the XLT and the XL4, they are designed to be able to mount to DIN rail. You don't have to mount them through the door of your enclosure. So that's another reason why the XLE can work great as a remote I/O block. Now let's talk about the screen. Now, in a lot of cases, when you're considering a small controller for an application, you might think that in your application as a user interface that the XLE falls short. That's because it really has a basic user interface that's not designed with a colored touchscreen or anything like that. So in some applications as a controller, you may want more as a user interface than the XLE delivers. But let's think about the XLE as a remote I/O block. What kind of user interface are we used to with remote I/O? Well, primarily LEDs for I/O status, network status, connection status, those sorts of things. Well, compared with just a few banks of LEDs, the XLE user interface is pretty extensive. So you can very easily create your own custom screens to provide I/O status for both digital and analog I/O, as well as high-speed counting if you've got that in your application. It can provide detailed network status, you name it, configuration information if that's what you're looking for. So again, compared with a remote I/O block, the user interface is not limited with the XLE, it's pretty extensive. Okay, now let's talk about the steps that are required to program the XLE as a remote I/O block. So what steps do I need to take in Cscape to get that done? Well, let's kind of go through them here. So first, you're going to select the I/O option that best meets your application requirements. So from a previous slide, you remember that there are 5 different I/O options available for the XLE. So you can choose from that list and kind of decide, okay, which one of these is going to fit my application the best? Do I have temperature sensors I need to interface to? Do I need relays or DC outputs? Those sorts of questions. How many analog channels do I have? How many digital channels do I have? And you've got a variety of options with the different XLE models that can really fit your application. Again, anywhere from 22 to 42 I/O points are available with the XLE as a remote I/O type device. So once you've decided which model you're going to use, now in Cscape you're going to configure that I/O because there's a lot of flexibility from a configuration standpoint with the I/O that you get built into XLE. On the input side, do I need positive logic or negative logic inputs? Positive logic's certainly more common, but maybe you need negative logic. Do I have high-speed counting in my application? Do I just need simple totalizing, or do I need to interface with encoders and have A quad B type interface? What about high-speed outputs? Any PWM or frequency requirements? Analog, of course, that needs configuration. Is it simply 4 to 20 milliamps I'm looking for, or do I need 0 to 10 volts or 0 to 100 millivolts, or maybe I have temperature sensors like RTDs and thermocouples that have to be integrated? What about my analog outputs? Do I need any? If so, do I need 4 to 20 milliamps, 0 to 10 volts? Do I need plus or minus 10 volts? Now, plus or minus 10 volts isn't available built into any of the XLE I/O models, but you can very easily get a under the cover plus or minus 10 volt analog output option, either 2 channels or 4 channels for any XLE model. So that's an easy way to add plus or minus 10 volt analog outputs to any of the XLE models. So from an I/O configuration standpoint, you're going to spend a little bit of time just configuring the specific I/O for your model to what you need. The next step really is going to be to configure the interface or the network connection that you're going to be using to connect to your PLC or your controller. So again, if you're talking Rockwell, that's probably Ethernet IP. If you're talking to a lot of kind of generic PLCs or other controllers, you may be talking about Modbus TCP. If it's an OCS, you're probably talking CSCAN or maybe Ethernet Global Data. So again, the specifics on the configuration are going to vary depending on which PLC or which controller that the XLE is being used with from a remote I/O standpoint. Okay, so once you've configured that network connection with the PLC or the controller, next you need to write just some really simple logic. And these are mostly move instructions and simple Boolean logic that's going to move your local inputs, digital and analog, over to areas where they can be available over the network. Whether that's available to be polled like they are on Modbus TCP, or whether they're sent out periodically like they are with Ethernet IP, for instance. And then conversely, on the other direction, the commands from the PLC or controller that are going to turn on your digital outputs or turn on or set the values for your analog outputs, that data coming in from the network needs to be copied over to your local %Q and %AQ type memory locations so that that data ends up turning on and off the digital I/O and setting the analog outputs as is appropriate. And then you're going to want to put a little bit of logic in there that just detects any communications loss with the PLC. And then if that were to occur, will put outputs, both digital and analog, in a safe state so that while they're not really under quote unquote control, they are in a safe state. So that's just a little bit of additional logic there. Again, really, really simple. And then finally, you get around to taking advantage of that screen that's available on the XLE that you don't find on any kind of remote I/O block, so that you can have some fairly extensive, put as much time into it as you choose, some fairly extensive diagnostic information, I/O status, emulating LEDs, putting analog values in there. You could even go to the point of having some configuration screens for changing things like the node address, maybe baud rate, those sorts of things. So again, you can spend as much or as little time as you like on the screen for the XLE to provide as much or as little kind of diagnostics or setup information as you choose when you are using the XLE screen. Okay, let's start with our first demonstration, and that will be our quick and simple setup. So getting the XLE up and running as fast as possible, specifically for your application with a minimum of bells and whistles. All right, here's the details on our first quick and simple setup. Now, the EXLW in both of our demos is going to be used as the main OCS controller. And we're going to be using an XLE Model 6 as our remote I/O block. Now the XLE Model 6 has a lot of I/O built into it, which makes it a really nice choice for this application where we're using it as a remote I/O block. It kind of replicates almost a whole rack worth of I/O in a single unit. So you can see the amount of I/O we have there, which is pretty substantial. I've also shown on the screen the memory locations where each of the 4 different I/O types is mapped in the XLE, because that'll come into play later. And in this first quick and simple demo, we won't be using the XLE high-speed counter. We'll try that out in the more comprehensive demo. Okay, now let's head to Cscape and let's see if we can implement this quickly. All right, so here's the program I've already created, but I'm going to show you kind of the steps. If you remember correctly, the first step was to select your model and do the I/O configuration. So we go to I/O configuration. We've selected our Model 6. That's what we want to use. We go to the local I/O tab. We press Config, Module Setup, and then we go through each of the 4 different data types or I/O types and configure it for our own application. Now in this example, I'm just using positive logic and I'm not using any counters. Of course, you would set this to match your requirements for your application, which is true for all 4 of these I/O types. For digital outputs, again, I'm leaving it at the default. I'm not taking advantage of any of the high-speed outputs. For analog inputs, I've just set every channel for 4 to 20 milliamps with a filtering level of 4, which is about a mid-level filtering. Now you could set these in your application to whatever type matches your application. And you can see the Model 6 supports a lot of different sensor types. On the analog output side, once again, I've set everything to 4 to 20 milliamps, and I've set it to go to 0 if the XLE would ever get out of run mode, for instance. Okay, so that's the I/O configuration, which you want to match your particular application requirements. Next, we need to configure the network that's going to be used to communicate with your controller. In this case, we've got a EXLW as our main controller here, and we're going to be talking to it over Cscan. So the XLEe is going to be a Cscan remote I/O drop. All right, so that means we have a little bit of configuration to do on Cscan. So let's go back to the controller tab, go to CAN1 and hit config. Now, we're going to want to make sure that network is required, because it is in this application. We're going to set it to network optimized, which ensures the most efficient transfer of data over the network. Our number of network IDs can remain at 1. We don't need more than 1 for this XLEe as a remote I/O block. But we are going to bump up our max packets per scan from 1 to 4. That ensures that regardless of what we need to transmit over the network at any given time, we can transmit all that data every scan of the XLEe. All right, so that's it for the configuration side of things. We have a little bit of work we still need to do on the network side, but we do it in ladder with Cscan. Okay, so let's start with a heartbeat. Now, anytime you're communicating over Cscan, whether you're an I/O block or just two OCSs communicating in another application, it's important that each device on the network generates a heartbeat so that the other devices on the network can detect that they're healthy, and if they're not, react as appropriate. So we're going to put a heartbeat out of our own ID. Okay, so since we're putting a heartbeat out of our own ID, I've chosen to use SR29, which is the network ID register. I also could have hard-coded it to 1 if I wanted to say this XLEe is always going to be an ID of 1. And I'm going to send that heartbeat out every 50 milliseconds. That's a good default time to use. Now, in addition to sending out a heartbeat, when I'm using an XLEe as a remote I/O block over Cscan, I want to detect the heartbeat of the main controller. So I use a net get heartbeat instruction. And then I'm looking for it from the OCS, which happens to be node 253. I want to make sure I see a heartbeat from that OCS at least every 100 milliseconds. Now, if I do receive a heartbeat on a regular basis, then I'm going to turn on this coil that I've created called main OCS OK. So that's what we're going to use as our main indication that the OCS is healthy. And if it's not, later on, we're going to take some steps to make sure our system remains safe. Okay, so that's pretty much it from the step of the network configuration. For local inputs, we need to send those out over the network so that the OCS can use them. And then conversely, the output data that the OCS sends to the XLEe needs to be received in and copied over to local output registers. So let's start with receiving data over the network and copy them to local output registers. Let's start with our digital outputs. So we're going to use a net get instruction to take the data from the network that the OCS is sending us and copy it to our local digital outputs. So let's take a look at the configuration of this net get instruction. All right, we're getting the data from the main OCS, which I've assigned an ID of 253. It's global data. It's digital data this time. It's the first digital data the OCS is sending us, so it has an offset of 0. And we're going to map it in starting at Q1 for 1 word worth of information. Okay, so that's where our digital output data, our local digital output data, is going to be coming from, and this is how we're going to get it mapped where it needs to go. Similarly, we need to take care of our analog outputs locally here. Okay, so we're grabbing data from that same OCS, this time analog data. The first analog data it's sending us, so it has an offset of 0. And we're going to map it into our local analog output registers. And those start from the XLEe data sheet. You can see those start at AQ9. So AQ9 through 12 because we're sending 4 words, or we're copying 4 words. Okay, now let's go the other direction. And that is the data from our digital inputs and our analog inputs that we need to send to the network so that the OCS can use them in its application, since the XLE is remote I/O. So we're going to put data to the network. We're going to put data using our own ID. We're sending it to the network under our own ID. So I'm using SR29. I could also have hard coded it as a 1. Sending it out as global data. I'm starting with digital data, the %I information. It's the first digital data I'm sending out, so no offset required. I'm sending data out starting at I1 because that's where the digital inputs are coming from with the XLE. And I'm going to send it on a change of state. This is very important. I don't want to send it every scan. I only want to send it every scan where the data has actually changed. And then if you choose change of state, you also have to choose another bit which you could use to send additional transmissions. I don't care about additional transmissions, so I'm just assigning that bit as the always off bit. And then I'm sending I1 and only one word of I1 information. So that'll be I1 through 16. Okay, so that's getting my digital input data to the network. Next, I have to get my analog input data to the network. Now, when I do that, I don't want to send my analog data on a change of state basis, because you could have a couple values just sitting there twiddling back and forth, and you're doing a lot of wasted transmissions. It's always better to send analog data on a periodic basis. So what I've done here is I've just, in a simple single rung, I've taken the internal S bit that turns on and off every 100 milliseconds, and I've created a one-shot that I can use to trigger the transmissions of my analog input registers. So it's coming from my own ID. It's analog data. It's the first analog data I'm sending, so no offset required. If you look at the XLE data sheet for the Model 6, it shows you that the 6 analog inputs come from AI33. Now on other models, they come from AI1, but not with the Model 6. And then there's 6 words that I'm sending because there's 6 analog inputs. Okay, so that's it as far as copying the data over back and forth for I's, Q's, AI's, and AQ's. The last thing I need to do is to ensure that if the main OCS goes away, that I set my local outputs and my local analog outputs to a safe level. And in my application, I'm saying that is 0. So if the main OCS is not okay, which means we haven't received a heartbeat from our heartbeat rung, then we're going to set Q1 starting at 0, or we're going to set 0 for Q1 through 12. It's actually Q1 through 16. Q13 through 16 aren't used, so it doesn't hurt anything to copy those extra 4 bits. And then we're also going to send a 0 to AQ9 through 12, which are the 4 analog outputs local. Okay, so that wraps up all the programming that's required. The last thing we have to do is, just as quickly as possible, remember we want to get this up and running with a minimum of time. The last thing we have to do is set up some screens that we can use to show local I/O indication. So I'll show you what I've set up here, and this is the bare minimum. So for my digital input indication, I'm just using a binary data field, which is going to show I1 through 12 as 1s and 0s. And I1 is right justified, and I12 is left justified, so I added these 1 and 12 labels here so that users know that it's right to left in terms of the indication. I've done the same thing with the Q1 through 12 by putting it directly underneath as another binary data field. And then lastly, for a simple status, I've added the main OCS OK indicator here on this screen. Most of the time I'm guessing this screen will be displayed, so at a glance you can see the status of the digital inputs as well as that everything is okay. Now of course the XLE has more than just LED indication, so I went ahead and added a couple quick and dirty additional screens for displaying the decimal status of my 6 analog inputs and my 4 analog outputs. And these objects over here are just jump objects for navigating from screen to screen. Okay, so that's it. That's all we've got programming wise. And I timed myself And this was probably about 30 to 40 minutes of programming and troubleshooting total. And if you're new to OCS, obviously it's going to take a little bit longer, but still not that much of an investment to get this started. And of course, you can always start with my program if you're going to try this out in your application. All right, let's take a look now at the setup I have here locally to run this application. So on the right is that EXLW, that is the main OCS. In the middle there is the XLE Model 6 that's being used as the remote I/O block. And on the left is an I/O simulator that I have wired to the XLE so that I can try out the XLE I/O. So I can go ahead and as I turn on inputs on my I/O simulator, okay, you can see the inputs turning on from right to left on my XLE screen and also on the far right top there on my EXLW screen as well. Okay. All right, you also should notice that the EXLW is exercising the digital outputs by kind of cycling them through. And you can see that happening both on the I/O simulator as well as the XLE indication. And then if I navigate to my analog input screen, you can see that as I tweak my analog inputs, it's changing on the XLE screen and it's also changing on the EXLW as well, if you look to the far right there. And then finally, as we look at the analog outputs, you can see that the EXLW is exercising analog output number 1. Okay, and that is showing through in the XLE. I'll also turn on my multimeter here to give an electrical indication of what's happening with that analog output controlled from the EXLW, but the actual physical output, of course, is on the XLE, which is being used as remote I/O block. Okay, so that's what we've got going here with our quick and simple setup of an XLE as a remote I/O block. Okay, now that we've shown you kind of the fastest way to get from A to B in terms of setting up your XLE as a remote I/O block, now let's take a look at a more comprehensive setup for using XLE as remote I/O with a few more bells and whistles and a few more options at runtime. And in either case, keep in mind that when we're done with this video, we will make available to you both the kind of quick and simple application program or Cscape file as well as the comprehensive one. So if you want to make this the starting point for your application, if you're going to use an XLE as remote I/O block, you're free to use this as you please. Okay, now let's take a look at our comprehensive setup. The basic elements are the same, but we did add high-speed counter support on the XLE. We also added an RTD channel. So instead of 6 channels of 4 to 20 milliamps, we now have 5 plus an RTD. We also made some things configurable on the XLE side instead of being hard-coded. The CAN ID and the CAN ID for the main OCS can now be set from the XLE screen, making that more adaptable to multiple applications. We also added some additional CAN diagnostics, some network traffic statistics to the XLE screen. And we spent a little bit more time in general on some nicer I/O status screens. And again, in your case, if you want to try this out, you can always start from my example program. All right, let's head to Cscape. Okay, now I'm going to mainly highlight what's different here. So again, starting with the I/O configuration, going to local I/O, hitting config and module setup. On the input side, I added a quadrature channel. Okay, so that is now used in this example program. On the analog side, channel 3 is now a RTD sensor. Okay, everything else is the same though from a I/O configuration standpoint. From a network configuration standpoint and just program organization in general, I broke the program up into multiple main loop modules. So starting with the first one, which is our heartbeat handling, this is basically the same as we did in our quick and dirty setup, but I did make the main OCS ID a register or a variable instead of being hard-coded. So that was the major change there. In terms of handling the %Q outputs, the local %Q outputs, because I added high-speed counter support, I also need to have at least one clear bit to clear that high-speed counter from the EXLW. So what I did was, in the quick and dirty example, we had 12 digital outputs that were driven locally or driven by the EXLW, but located locally in the XLE. And then there were 4 extra bits that weren't being used that the EXLW was sending. In this example, because we needed to send a clear bit for the high-speed counter, I went ahead and tacked those 4 bits onto the 4 previously unused bits before. And then instead of copying those directly into the Q bits using the netget function, instead I copied those into local T bits and then moved the T bits over to the Q bits. That gave me the flexibility of handling these clear bits a little differently. Okay, but the end result is the first 12 bits from the network are local outputs. We've also got some high-speed counter clear bits that we've tacked to the end there. Okay, so little differences there. Let's take a look at our local analog outputs. No significant changes there. Let's take a look at our digital inputs. Not a lot of changes there as well. And then the analog input side of things, I did things a little differently here. From the standpoint of the frequency at which we broadcast our analog input data to the network, I made that configurable on the XLE screen in milliseconds between 10 and 100. So I've got a little logic here that takes the data that the user plugged into that screen, and I'll show you that screen in a minute, and basically makes sure that it's within limits between 10 and 100, and if it's not, I set it to a default value of 50. So if it's not set by the user, we're going to transmit our analog input data every 50 milliseconds to the network. And that's really all this logic does here. And then here's my net put. Again, triggered a variable amount of time between 10 and 100 milliseconds. I'm sending my 6 pieces of analog input, or my 6 channels of analog input. Now, because I supported high-speed counter here as well, I've got a 2-word accumulator for my high-speed counter. And if I had multiple high-speed counters, I'd have multiple accumulators. So I have an additional net put sending the additional 2 words, the 32-bit accumulator, to the network. Now notice, let's review these real quick. The first 6 words of analog data that I'm sending to the network are my 6 analog input channels. So this is basically identical to what we did in the quick and dirty example. However, because I'm sending additional information on top of that, for this particular net put, I have an offset of 6 because it's not the first 2 words I'm sending, it's the 7th and the 8th in this case for the high-speed counter accumulator. So this is where the data is coming from. That's the high-speed counter accumulator register, and I'm sending 2 words, okay, again, with an offset of 6. So those are some slight differences there in my logic. All right, now a lot of the differences are on the screen. So let's take a look at those screens here. Okay, so you can see we've got a little bit of a menu set up here where I have a main screen and the user can jump to either status or setup. Let's go ahead and navigate here. Let's go to setup first. Okay, so on my setup screen here, I have local CAN address that can be set, as well as the OCS's CAN address that can be set from here. And then here's where I set my analog update rate for my analog input channels between 10 and 100 milliseconds. All right, so that's my setup screen. Let me go ahead and navigate back to my main screen here. Now let's go to our first status screen. On our first status screen, we can choose between CAN status and I/O status. Let's take a look at CAN status because there were quite a few changes there. Okay, we go to CAN status, and now we've got 4 pieces of information for CAN status. We have the main OCS OK, which we had on our previous example. We also are using the CAN OK bit, which is a system bit. And then we've got some local system register data for the local traffic being generated by this XLE, as well as the current total traffic on the network. So that's some additional useful information that I added for this more comprehensive example. All right, let's head back to our status screens. Now we've looked at CAN status. Now let's take a look at our I/O status. And these are a little bit more user-friendly. We have individual blocks or LEDs for each of the 12 outputs. Okay, I also used a down arrow here, kind of as a graphic on top of my jump instruction to kind of give that a little nicer look there. You can see I used these reverse text titles on each of the screens. And you see we had digital in, now we have digital out. We have analog in, all 6 channels, analog out, all 4 channels. We also have our high-speed counter accumulator. Now another thing you may or may not have noticed is that these numbers here are a little bit smaller. Okay, and that's because I went ahead and used a tiny font. We have a 4x6 tiny font that's available in the OCS. I went ahead and went to the OCS font manager. Let me show you that real quick. So if we go to the, I think it's under Tools, Font Manager, I went ahead and added the tiny 4x6 font to the project so it would be available. When I went ahead and double-clicked here, you can see I have the option between 5x7 font and tiny 4x6 there at the bottom. Okay, so that's an additional option now that I didn't have before. Okay, so that is the changes that were made to the screens. All right, now let's take a look at what things look like on our demo. Okay, we'll go ahead and navigate. You can see things pretty much look the same as before everywhere except for the XLE. Let's take a look at our setup. Okay, there you can see we've got the local CAN ID set to 1 and the OCS CAN ID set to 253. I can use my arrow keys here to navigate to my different objects. I can also use Escape to return to the previous screen. That's what I've implemented with this particular demo. Okay, we can also take a look at status. Let's take a look at that CAN status. Okay, there we can see our local network traffic we're generating is about 4%. Our total network traffic is at about an 8% level. So pretty fast updates and no significant impact on speed. But let's bump it up a little bit and see how that works. Okay, I'm going to go back here to my setup. Okay, so I've changed my update rate to 25 milliseconds, made it twice as fast. Let's see how that impacts our network traffic. As you can see, we're definitely using more network bandwidth than we were before, but not a crazy amount. All right, let's check out our I/O status screens. A little more user-friendly there. And we probably could have added additional labels, but that's pretty user-friendly, I would say. There's the status of our outputs. We can see those changing. Our analog input values. And our analog output value. And you can see down here on my multimeter that analog output value is still cooking along like it was before, but even updating even faster because we're updating it. Oh no, that's not being affected by our update setting. That's only for analog data going to the network, to the EXLW. Okay, so that's our more comprehensive example. Again, I hope you found that useful. Okay, that wraps up our topic for today. And I hope you found it enlightening, or at least it gets you thinking a little bit outside the box. That might help you solve that next application when you've got a supply chain issue. So remember, we're here every Tuesday at 2 o'clock with another new topic. If you watch us live, we'll have experts standing by to answer your questions in real time. And as always, if you watch us on replay on our YouTube channel or from our website, you'll have the opportunity to get your questions answered just through the comment section and not quite in real time. Next week, we've got another good topic for you. It's kind of related in that we'll go into more details about using an OCS, like an XLEe or another OCS, as an Ethernet IP I/O adapter. Now, in this scenario, you'll probably still use the XLE or the XL4, whatever the OCS is, as a full controller, but you'll have the ability for that section of the machine or that piece of auxiliary equipment to talk seamlessly with an Ethernet IP scanner like you might find on a Rockwell PLC, for instance. Couple more things. First of all, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications, you'll be notified every time we go live or every time we post a new video. Okay, stay safe out there.